Our first step in solving this myth was to try to get a penny to float inside a wind tunnel, thus reaching its terminal velocity. An object reaches maximum velocity when force of air resistance equals the force of gravity. In other words, when there is zero net force. The team immediately ran into a problem though. We couldn't get the penny to stay inside the tube. So, instead, we used a more massive object, an eraser. To measure the wind speed that the object was floating at, we created a calibration scale, taped it against the tube, and sent a small green, essentially massless, piece of paper through the tube and filmed it with a high-speed camera. Analyzing the video, we could determine the paper's velocity and thus the wind velocity. We compared this calculation against the readings from an anemometer and found a factor of 2 error.
Alright, what do we got going on here?
Well, we're trying to get the eraser to hover to find its terminal airspeed velocity, and then we're going to launch a piece of paper up alongside it.
Alright, so we're going to try and find the terminal velocity of that eraser right there, and then while that's still in the wind tunnel, floating like it is right now, then we're just going to send a little piece of paper up there with, and use the high speed to see like what the velocity is. And using our very scientific honors physics method of duct taping that are rigged together, we should get some results hopefully here pretty soon.
We're trying to make at least a partial seal at the bottom.
Partial seal at the bottom. Alright.
Is that enough to launch that through?
And he's putting the paper in, and it's good. Alright. Looks good. Let's try and do the full experiment.
Piece of paper going from like a certain distance.
Going from right now to right now.
Right, and we know the camera takes pictures at 300 frames per second, so it was 3 frames that we used, or 1 frame?
One frame
that we used, and then it traveled 3.9 centimeters divided by 1/300th of a second, and then you just convert that into miles per hour.
It's math. And now that we know that this wind speed is well below the limit of the anemometer, we're going to turn on our wind tunnel and take another measurement.
Hey Corey, what's Tracker and why are we using this?
Alright, Tracker is a program that monitors motion through film, and it allows you to see how fast something is going and how much movement it has and its speed and velocity and all of that. And we're using it to track the piece of paper that we put through the wind tunnel to see how fast the penny is going. And here you can see as it goes along, these are dots detecting the motion of the piece of paper, and you put 1 at each frame, and with the frames per second and the reference frame that we put in, it's able to tell you the motion that the piece of paper has. And from this graph, you can tell the final speed, or the average speed of the piece of paper through all of it, giving us what we think is the average speed of the air that the penny's traveling at.
Uh-oh, there's a huge difference in our numbers. What will the team do now?
What's going on?
It's a sad day in the honors physics section. That's what's going on. Either the software is throwing off our measurements that we made with a high-speed camera, or the anemometer is wrong. So,
Well, I mean,
like,
we've seen the variations in the anemometer from just the different positions that it was in.
Holding
yeah.
it up half a centimeter will change it by 10 miles an hour.
Okay. So,
Which
Professor-
means, I mean, if we were holding it slightly above the tube while we were doing the eraser and we're getting 50, that means if it's right on it, that we're going to be up to 65-ish. And that's going to be too close to the anemometers.
So, what we're going to do is Professor Quartermeyer suggested this is we're going to do kind of like a control run. Like we can set up the cart right there, and we can measure the velocity with the motion sensors. And then, but while we do that, we can record it with a high-speed camera, and then compare the velocity that we know and the velocity that we get right here.
Now that the team knows the camera is working properly, they take to the stairs to determine from freefall the penny's terminal velocity.
Okay, so over there we have a scale to measure how far the pennies go and like the distance that they travel over a certain amount of time. And this is our light, and this is our HD camera, so hopefully our pennies make it down.
So now we're actually doing the dropping of the pennies, and we dropped about 30 pennies down this tube to try to get one down to the bottom, just because there's so much air with the wind and everything, and then just the distance that it has to fall. So I think we got 2 or 3 pennies out of those 30 that hit the ground.
3, go. I saw them go perfectly straight down.
So, we're going to take this liquid nitrogen and add really hot gross water to it, and hopefully we can see the smoke.
Thanks to a little help from chemistry, the team finally gets some good data. After weeks of hard work, with many ups and many downs, the team finally calculated the terminal velocity of the penny within 3 miles per hour. We'll take it.
The momentum of the penny was 0.028 kilogram meters per second, which is less than 63 kilograms meters per second, which was the momentum required to fracture the cadaver's skull.
Myth busted.
Myth busted. Boom.
Now that the team has finished the penny drop myth, they decide to do something a little different.
So for the kind of like a follow-up to the penny drop myth, we wanted to figure out if a calculator was dropped from a tall building, would it kill you by the time it hit you? So
Mass of the calculator was 241.8 grams or 0.2418 kilograms. Its maximum velocity was 18.32 meters per second. The momentum we calculated, 4.430 kilogram meters per second, which was in fact much less than what was required to crack a human skull.
therefore, calculator drop from the building won't kill you. Myth busted.
In order to test this myth, we need to throw an object out of a moving vehicle, which requires us to leave the lab and go outside.
I see what you did there.
For this to work out, the team will travel in a car at a velocity v and will have to throw a ball at an equal velocity in the opposite direction. Because of this, the magnitudes of the two vectors will be equal, and if all works out, will cancel, making it appear to an observer that the ball will drop vertically to the ground. Huzzah!
No. No get. There goes the ball. Another failed attempt by Graydon Donald Barnes.
Tell the camera that because you're using the pink ball.
Close. We're so close to actually getting it.
Because you're using the pink ball.
As seen by the artistic representation of our experiment, drove along at a constant velocity, and then we let the wind basically catch our arm to make sure that the ball was thrown back at the same velocity that the car was traveling.
When this happened, the ball appeared to fall straight down. Therefore, myth confirmed.
Boom.
This is Jeff. Jeff is a calculator. Jeff has survived many falls down flights of stairs.
Probably like at least half a dozen flights, at least half a dozen drops down the stairs of Holmes Hall. And now, after testing our car myth, we're going to see that, like, if the myth holds true for calculators as well. This may be our final moments with Jeff.
Let's remember him fondly. Jeff was a very faithful calculator, loyal to the end. He's very hardworking. We will all miss you, Jeff, in your final journey through life.
I love you, Jeff!
I love you, Jeff.
We'll be thinking kindly of you as we watch you smash against the ground. We love you, Jeff.
Goodbye, Jeff! You know, I always wondered why Professor Quartermatter had such a hatred of calculators. Now, I think I can hazard a guess. This calculator is obviously possessed by something. It just got thrown from a car twice. Jeff is alive and well. Still. Oh God!